Sweden with a German Ministry of Education and Science. So of course, also these webinars are an excellent possibility to maybe find future collaborators. Yes. So it's exactly. Yeah, and I think especially between the Nordic countries and Germany, there's possibilities.
So now it's time to start this webinar. So welcome everyone. Welcome to you who are joining us at Zoom, and welcome you who are following us on YouTube. And a special welcome to our speaker, of course, Dr. Katja Heise. So we have Professor Lars Wågberg here as well, and Professor Annette Larsson, who will make sure that we handle our questions, any questions that you in the audience have. And Professor Wågberg will also give an introduction. And about question, if you have any questions, please you use the chat or the Q&A function in Zoom, or if you're on YouTube, you can use the live chat. Now I see that we might have some problems with YouTube. So that was, of course, unexpected. But anyway, you are here on Zoom. So I leave the word to Professor Lars Wågberg.
Thank you so much, Josephine. And I will be very brief. It's a pleasure to have Dr. Katja Heise with us today to talk about the spatioselective modifications and analysis of fibers and cellulose in all its complications and beauty. But so it's a pleasure to have you with us. And Dr. Heise has had an Academy of Finland postdoc grant, being at Aalto University. And also now I heard from Eero Kuntonen, whom you have been working with, that you also have received the German grant for building up your own research team in Germany. So we're happy to have you with us, and we hope that this will be a start of some future cooperations or collaborations. Katja, the screen is yours, and thank you for joining us.
Yeah, thank you very much for the very nice introduction, and especially for inviting me. And I feel really honored speaking here, seeing also the lineup of very excellent and also experienced researchers before me. When I was asked to speak about like thermoplastic properties or thermoplastics, I thought that actually I'm doing the exact opposite, because I'm working with something that is highly crystalline and doesn't have thermoplastic properties at all. Nevertheless, I think like the chemistry I will be speaking about today might be interesting for many of you, and also especially the analysis. And this work has been like carried out throughout the last years, and that's of course not only my work, even though just my name is standing there. It's like a whole group of excellent researchers standing behind that. And as Professor Wågberg has said already, I'm currently a postdoc at Aalto University in the group of Eero Kuntonen and also Mauri Kostiainen. I'm still funded by the Academy of Finland, but from January 23 on, I will be moving to a small university in Eastern Germany at TU Freiberg, and I will start my own research group there, which will be working mostly on like materials for membranes and also electrospinning. And I'm of course very happy to like talk about also collaborations in the future, and also to welcome you maybe there in Freiberg for a short visit. Okay, but let's get started. So I want to talk about spatioselective chemistry and also NMR spectroscopy. But first of all, I would like to very, very shortly speak about the top-down isolation of cellulose nanocrystals and their anisotropicity. And then I would like to introduce to you NMR spectroscopy, so liquid state NMR spectroscopy in ionic liquids, and why this is actually the new level of molecular analysis for crystalline biopolymers. And then last but not least, I would like to speak a bit about the spatioselective modification by the example of reducing end group modification. Okay, so many of you know, or most of you probably know, that we can isolate cellulose nanocrystals from plant cell walls. We can also, of course, obtain it from bacterial cellulose. From the plant cell wall, we have our typical hierarchy from fibers to fibrils. The smallest unit are our elementary fibrils. And if you only take the crystalline section out of those, you obtain these rod-shaped particles with high crystallinity, which are cellulose nanocrystals. And if you take the whole elementary fibril, you obtain semi-crystalline threads that are, of course, also semi-flexible. And what they, of course, both have in common is that they're built up from cellulose, which already has a molecular anisotropy. So you have reducing end groups on one side and the non-reducing end groups on the other side. Probably the most common pathway to isolate cellulose nanocrystals is sulfuric acid hydrolysis. If you start, for example, from cotton filter paper, you use 64 weight % sulfuric acid, and you obtain these nice bluish dispersions, which are already like a sign for the excellent colloidal properties of cellulose nanocrystals. What happens during hydrolysis is that the acid actually assesses the disordered, so the amorphous regions of our fibrils, and this leads to hydrolysis and to the to cellulose nanocrystals. And these are rod-shaped particles. As a consequence of the sulfuric acid hydrolysis, we have sulfuric acid half-ester groups on the surface. So we are essentially not working with pure cellulose already, at least on the surface, we have a derivative. And we also have hydroxyl groups, of course, on the surface. And speaking about spatioselective chemistry, there are, of course, also pathways for spatioselective chemistry on OH groups. There's recent publications from Marco Beaumont from BOCO in Vienna. But what I was much more interested in, together with my collaborators, was to modify reducing end groups. So due to the biosynthesis of the cellulose, all chains are synthesized in the same direction, which results into all reducing end groups pointing towards one direction. And this enables Janus type modifications. So if we attach new functionalities to the reducing end groups, we end up with Janus type particles. And this all sounds very simple. So we have anisotropic particles, we have an inherent directionality of our cellulose nanocrystals, but we have significant or major synthetic and also analytical challenges. For the synthetic challenges, we of course want to target aldehyde groups, but those are in equilibrium with the closed ring hemiacetal forms. And this equilibrium, called mutarotation, is largely on the side of the hemiacetal groups. So we need chemistry that is actually able to activate our reducing end groups, so to liberate our free aldehyde groups for the later modification. And this can be done by acid-base catalysis, or already, as it is shown here on the right side, already by one water molecule that is catalyzing the ring opening reaction. The second challenge, and this is what I will discuss in the next minutes, is actually an analytical challenge. So we have a substrate that is highly crystalline. Cellulose doesn't dissolve in common solvent systems, which of course is complicated for NMR spectroscopy, for example. And we have a very low abundance of newly introduced functionalities at the reducing ends. So how can we actually analyze now and confirm also modifications on cellulose nanocrystals, and especially the spatioselective modifications? And for this, we are actually really lucky. We have a method available. We have a solvent system available. It's a method that has been published in 2018 the first time. The expert behind this, of course, Alistair King. He's now at VTT, and also Tatjana Koso at the University of Helsinki. And they have developed a method where they use an ionic liquid electrolyte with DMSO as a co-solvent to dissolve cellulose nanocrystals, and then carry out high resolution 1D and 2D NMR spectroscopy. And what I can tell you is that the resolution is good enough for even like observing and confirming modifications at the reducing end groups with this low abundance of newly introduced functionalities. And I don't want to go into detail with the method now. I don't want to torture you too much with NMR spectroscopy. I just would like to give you a few examples on why this method could be actually also useful for you. And I also, at the same time, would like to also advertise our protocol that will be published hopefully soon in Nature Protocols to you. It's a summary of all methods. And it's really meant to that researchers can take it. So cellulose chemists, for example, can take it as go-to analysis. And you have described the synthesis of the electrolyte in there, and also the whole NMR procedure with a lot of details. Okay, but why do we use this method? Why are we so interested in that? So what you see here on the bottom of the left side is a standard solid state NMR spectrum. It's CPMS carbon spectrum of microcrystalline cellulose. So we have cross polarization magic angle spinning, which already should give solution state like a spectrum. However, of course, we're working with a polymer. So what we observe is that we don't have proper resolution of all cellulose backbone signals, and we also have peak broadening. If we use now our ionic liquid electrolyte, we can do solution state NMR. We have well-resolved spectra, and we also have quantitative information. So yeah, we use it for high resolution analysis. And what we can also do is that we can actually confirm covalent modification. And this is very often the case with solid state NMR, is that you modify your cellulose, but you cannot really distinguish in many cases between surface adsorption of a compound and real covalent modification. And this is something, I will show you the technique for it in a few minutes. This is something we can do with solution state NMR, of course. You can also calculate a decrease of substitution after modification, and you can also obtain from solution state NMR the degree of polymerization. And moreover, if we use cellulose nanocrystals for studying reaction chemistry, we can also use them as a model compound for studying the reactivity of cellulosics. What do we need? Like, the sample, of course, needs to be soluble in the electrolyte and stable. The electrolyte is slightly basic, so it's of course sometimes a stability problem. We also had solution problems with highly charged nanocelluloses, but there's some ways around that, also described in the protocol. You need at least 30 to 50 milligrams of sample, and because it was found out that the protocol works really nicely with 3 to 5 weight% solutions, then you have a reasonable viscosity for also handling the samples and good signal to noise ratio for your spectrum. There are some limitations. So if we study reaction chemistry to understand that and to properly assign the signals, we very often need model compounds. We use for that cellobiose or glucose. Then the measurement and also the dissolution of the cellulose is carried out at 65 degrees, which can be a challenge for the samples, but also for the spectrometer. And this is something that the NMR expert, of course, has to check whether, for example, the probe is made for these high temperatures. We have relatively long measurement times, depending on which 1D and 2D NMR spectrum I want to acquire. So can be up to 12 hours. And if we have pulps, for example, in high molecular weight, we might observe peak broadening, but I will come to this also a bit later. Okay, the solvent system that we use, as I mentioned, is an ionic liquid. It's tetrabutylphosphonium acetate, which is used with a co-solvent DMSO in a ratio of 1:4. This electrolyte can be obtained through like an optimized protocol now by Lukas Flere from Aalto University through a silver metathesis. And there have been like several ionic liquids that were studied in this regard. However, this one was found to not degrade the cellulose, also yield reasonable viscosity, as I mentioned, at 65 degrees for sample handling. And which is very important, the ionic liquid signals outside the cellulose backbone signals. And it's also now commercially available, even though it is very expensive still. And seeing the protocol, you can also do it easily by yourself in your labs. So in further dissolution procedure, so we use our 30 to 50 milligrams of CNC sample or cellulose nanocrystal sample. We dissolve it mostly overnight at 65 degrees already under stirring. Then in EUC, when the solution is not yet really clear, so what we're aiming for, of course, are clear solutions. And then we know we can go to analysis. And how does this look like? So this is a carbon spectrum on the left side of microcrystalline cellulose. And as I said, like the ionic liquid signals are nicely outside of the range of our cellulose backbone signals, which are also nicely resolved. If we go to our proton spectrum, we see the same thing. So we have here the standard proton spectrum on top, which has nicely resolved backbone signals. However, if you now modify, for example, with alkyl chains on the surface, you might need to get rid of these ionic liquid signals because, of course, they're overlapping with what we actually want to observe. And this is when one technique that is also a key technique for our experiments comes into play, which is diffusion editing. So to resolve, for example, the alkyl region. And it's an experiment that is based on diffusion coefficients. So it's diffusion ordered spectroscopy, or DOSI. And what we can basically do is that we distinguish the diffusion coefficients of slow or polymer compounds to fast diffusing low molecular weight compounds. So why do we do this? It's also described in Alistair's article from 2018. We do this to edit out, first of all, our ionic liquid signals, also the DMSO, and also residual water, and also to get rid of all adsorbed compounds on the cellulose surface. So with this method, you can actually really say something is covalently attached. Okay, one other important aspect if you are thinking of, you have this and this spectrometer available, is that maybe suitable. What is of course important for the result that you get for your spectra is the spectrometer field strengths. So Alistair has tested like different spectrometers from 400 megahertz to 850 megahertz. And of course, if you increase the spectrometer field strengths, you increase signal to noise and your spectral quality. This might be especially relevant when you have high DP samples. So for example, pulps with high molecular weight, and also low concentrations. And of course, also if we modify reducing end groups, it improves like the quality of our spectra. Alternatively, what you can of course also do is that you use different probes. So what they have tried is the use of cryoprobes, for example. And also if you, for example, that's something that we have at Aalto, we mostly work with a 400 megahertz spectrometer. We increase the transient scans. So with a scan number, of course, I can increase my signal to noise ratio and my spectral quality. And yeah. So then I mentioned that, of course, we use it now for cellulose nanocrystals. We have very nice spectra for microcrystalline cellulose, but you can also use this method for pulps, for example, so for high molecular weight samples. For the low molecular weight or low DP, the spectra are well resolved. So these are the three ones here on the top. You get quantitative information. You can calculate a degree of substitution after modification, also DP values. But if you have, for example, high molecular weight or high DP samples, you have a viscosity increase. So sometimes it's difficult to actually handle your samples. You observe peak broadening. So it might be actually necessary that you reduce the amount of cellulose in your sample to 2.5 weight%, which is still possible. Then you get like reasonable spectra, but you lose the full resolution of your signals, so the quantitative information, but you can still estimate, for example, compositional information, so like hemicellulose contents. So it's widely applicable also to pulps. And not even only to pure celluloses. So you can, as it is shown here on the left side, you can also use it for full wood fibers. So after diffusion editing, for example, you can identify then also signals of hemicelluloses and also the lignin aromatics and also the different lignin linkages. And Alistair and his team, they have even used the method for proteins, also for whole insects, even though we have to say that, for example, chitin is not fully soluble. So if you're interested in this method and if you're seeking for collaboration in this regard, I mentioned already that University of Helsinki has a very nice setup. They have cryoprobes for very good spectral quality and also spectrometers with up to 850 megahertz. You can contact for that Tatjana Koso or Alistair King, who's now at VTT. At Aalto, it's Lukas Vlieri would be the one person to contact, and he's in the group. He's a PhD student in the group of Michael Hummel. And also I'm aiming to also implement the method at TU Freiberg in Germany. So potentially soon we will be also able to use the method. But as I said, once the protocol is out, I hope that a lot of people will be able to actually implement this method on their spectrometers. Okay, so how can we now use it to confirm spatial selective chemistry? Because that's the topic of this talk. First of all, coming from the other side, the modification of reducing end groups as a spatial selective approach was initially used to actually demonstrate the directionality of cellulose. So it's something which they have done already really early in the 20th century. What they have used is a silver labeling approach to also be able to use microscopy. So for microscopy, you of course need a bulky functionality to attach to the reducing end with a very good contrast. What I'm much more interested in is the chemistry behind. So for the silver labeling approach, they use a thiocinic herbicide to attach it to the reducing end groups. And I'm much more interested now into the molecular information that is necessary for that and really the modification of the cellulose. So what I will be talking about now is a little bit like the reactions that we can use, especially by one example, and also the analysis, so the NMR analysis applied to the spatial selective modification. And then last but not least, why is this actually interesting for from a materials viewpoint? Okay, so this is something you have seen before. So we have our cellulose nanocrystals with reducing end groups pointing to one side. These are in equilibrium with our hemiacetals. So what we need is either acidic or basic pH or high temperatures in the presence of water to really activate the ring opening. And then we use aldehyde-specific chemistry. So the chemistry we can use is, for example, a ligation reaction. This has been done with hydrazines or hydrazine derivatives and hydroxylamine derivatives. What you obtain are hydrazones and oxazones. The reactions are carried out in water at acidic pH, and they work really nicely. A second possibility, it's known from monosaccharide or disaccharide chemistry, is the use of decarbonate compounds in the so-called Knoevenagel condensation. And what you obtain are ketone functionalities on your reducing ends. And these reactions, I will go into a bit more detail with this one later, are carried out in water and at basic pH. And the third possibility, it's something we've been studying quite widely with Gwendoline Delpierre, is the use of primary amines to attach them under reductive conditions to the reducing end, and what you obtain are secondary amines. So it's really interesting for bioconjugation, for example. Okay, but let's talk a bit more about the Knoevenagel condensation. It's a reaction we use more or less as a proof of concept. So first of all, can we translate this monosaccharide chemistry to a complex substrate, so cellulose nanocrystals, and can we also use our NMR method to really analyze these products? The reaction itself is super easy. So you basically just take your freeze-dried cellulose nanocrystals, you redisperse them in sodium bicarbonate solution. As a demonstrator, we used a very simple dicarbonate compound. It's acetyl-acetone, or ACAC in organic chemistry language. You can also translate these to other dicarbonate compounds. The condensation reaction is carried out at 80 degrees and overnight, and then you have a very simple workup just with water and by dialysis to obtain the ketone modified cellulose nanocrystals. The reaction itself goes over several intermediate stages, and the only side product that you have, it's water, of course, it's a condensation, and also sodium acetate. So the aqueous workup is really easy. And what you end up with, as I mentioned, is the keto functionality on your cellulose nanocrystals. NMR spectroscopy, as I said, like if you want to comply to organic chem standards, can be very complex in terms of confirming your reaction and also like to really properly assign your signals. So in this case, and to improve that, we use Cellulose as a model compound. It's very easy to use this because it's soluble in water. You can do very simple analysis and also signal assignments. So what you see here on the left, on the right side is the bottom spectrum, standard proton spectrum of Cellulose. And you can also identify the different anomers of the sugars, so the alpha anomer and the beta anomer. And on top, you have the Cellulose ketone. And then you can immediately identify your methylene group signals and also the new signal introduced for the methyl group of the ketone functionality. Once this works, and also the reaction work, you can translate the conditions and the analysis to cellulose nanocrystals. And then we have, like on the top still, our standard proton spectrum of our Cellulose with the identified signals. And on the bottom, you have the diffusion edited spectrum of our CNC ketone, where you can identify the same signals, of course, with a far lower abundance. And now the interesting question is, because as I said, we can quantify with our method. Can we actually really quantify? And this is something, don't get confused with this image, looks a bit complex. It's something we can do with a method, a FitYK, however, with limitations. So what we normally do to treat our spectrum, we do baseline correction, and then we select the necessary signals. In our case, we use the ratio of our polymeric C1 proton compared to the new keto functionality, and we deconvolute these signals and use the areas. This is something that could work, of course, for standard proton NMR spectroscopy. However, we lose this quantitative information for our diffusion edited spectra because of the faster relaxation of the cellulose backbone, because it's very stiff compared to the ketone functionality we attach later or any other substituent. We overestimate the signals of our new substituent, so of our ketone functionality, by a factor of 2.4. So it means we lose quantitative information. What we can still do is that we estimate the degree of substitution. And this was for the ketone functionalization, it was a bit disappointing because seeing that we used a huge excess of reactants, which is very often the case for cellulose modification, and we only had a conversion of less than 20%. If you want to have reliable quantification of reducing end group modification, you go back to the wet chemistry methods. This is one example. It's a fluorescent hydroxylamine that is attached to non-modified reducing end groups or like the pristine cellulose nanocrystals. And you can then quantify this derivative by fluorescence spectroscopy. You can also couple this with GPC measurements. And it's a method that has been developed by Antje Pottas and Thomas Rosenau at BOKU in Vienna. And this works really nicely. So we always use, compared to our, together with our NMR spectroscopy, we use complementary methods for a proper analysis. Okay, now we know that we can modify reducing end groups, we can analyze them. But why do we actually do this? Why are we interested in that, in this spatial selective modification? And I can tell you that the ideas behind that are purely conceptual. There's no scale up yet. We still struggle with this huge excess of chemicals. I was asked recently, like, is this actually sustainable? And this is really the question. And this is for future research, definitely. Nevertheless, from the material side, it's really interesting because controlling really the surface chemistry at the molecular scale leads to controlling colloidal properties in the nanometer scale and also micrometer scale, and then finally to the design of functional materials with nanometer and isotropicity due to the spatial selective modification. So in terms of molecular scale controlling or tuning, we can, for example, as I mentioned before, synthesize these Janus type constructs. So we attach something to the reducing end with completely different physical-chemical properties. It's something that I've been working together with Gwendoline Delpierre on. We crafted polymers to the reducing end groups. Then in terms of controlling colloidal properties, there's a very interesting work, or several works actually, of Bruno Jean and his co-workers, and they have tailored self-assembly by crafting temperature responsive groups to the reducing end groups of cellulose nanocrystals, and above the lower critical solution temperature of the polymer, they have these nice star-shaped assemblies. And from the materials perspective, we have applications in composites, also electronics, and also in sensors. Sensors is more like the direction which is shown here. It's a relatively recent work of Chemont and co-workers. They have crafted pH responsive dendrimers to the reducing end groups and then assembled those on QCM sensors. And then they basically show by QCM the pH response. So really interesting concept for maybe sensor applications in the future. Okay, what we did, I just want to very, very briefly show this with Quen is polymer crafting at the reducing end groups. It's a work from last year. So we use atom transfer radical polymerization because it's very controllable. And for that, the key step is that we actually really selectively attach a polymerization initiator to the reducing end groups. We do this with reductive amination, and then we craft polymer chains from this generated macro initiator. And what Quen was then interested in, and coming back to also the material concepts, is can I actually, by crafting polymer chains, the reducing end groups, can I tune the liquid crystalline properties of cellulose nanocrystals? And yes, it's something that she can do. So she has crafted polymer chains from cellulose 1 nanocrystals with reducing end groups only on one side, and also cellulose 2 nanocrystals, where you basically have anti-parallel chain alignment and you have reducing end groups on both sides. So after polymer crafting, you get this dumbbell structure, and she has really shown in this work how she can actually tune the liquid crystalline properties. So I really recommend reading this article. Okay, what is the big picture of that? So why are we in general interested in modifying cellulose nanocrystals? I mean, we are currently really in the transition from like semi-industrial production to industrial production of cellulose nanocrystals. The market volume is really significantly increasing, with up to $850 million by 2025, the forecast. And of course, all the global players, which were originally in paper industry, and that's something you know much more than I do know it, like UPM, Stora Enso, and also German companies like Jena Cell, they're interested in nanocellulose and also in products made from them, like cosmetics, like this face mask, which I found very interesting, and also wound care products or packaging. And of course, for these concepts, we still need like research to be carried out, and especially, and that's why I was also talking about scalability and sustainability of chemical modifications, we need to also keep this in mind. Yeah, that's critical about the spatial selective modification, but we are working on that in the future. And with that, I actually would like to again emphasize that research is teamwork. So I'm really lucky that I've been in two very excellent teams at Aalto University. So the group of Eero Konturi and also the group of Mauri Kostiainen. And I've been working with really, really nice collaborators from BUK in Vienna, from the University of Helsinki, but also from UBC, from Fribourg, and also would like to acknowledge the funding from Academy of Finland, and also my hosting institute now at TU Freiburg, which is the Institute of Electronic and Sensor Materials. And with a few impressions from Finland, so if you haven't been there, you should go there because it's a lovely country. I would like to thank you for your attention, and I'm really happy to discuss this with you. Thank you very much.
Thank you so much, Katja, for a very, very nice presentation. And there must be questions. Do we have any questions around?
So far, not in the chat, Lars, but
maybe I can start off a bit. We have had Per Larsson, who is in the audience here. He has been developing a technique for making thermoplastic fibers by ring opening of peridate oxidation to make dialdehyde groups. But then we have had big problems in determining the molecular mass of the DP of the cellulose due to, well, different solubility properties. So with the technique that you have with us, have you seen how the solubility effects will change your methodology a lot, or do you have any comments on that?
I suppose that you have cross-linking problems, right? After peridate oxidation.
Not cross-linking problems, but
within the chains because of the hemiacetal formation.
Yes,
right?
we can. That's how we use them. That's how we use the fibers.
Yeah.
Per can chip in on that, but we would like to see how the oxidation affects the molecular structure if we are breaking down the polymers or not. And this is a problem for us. But would this be a possibility of using the solvent that you're using for determining the DP, for instance?
Yeah,
certainly.
Certainly, it's something that actually Lucas Freire is also working on. So he would be definitely a person then to ask, because I know that he's also doing the solution state NMR on these samples. And yeah, it is challenging because we had like with several different samples, we had solution problems. It really depends, for example, if you modify and then you have like cross-linking between chains during the modification, then of course it's impossible to dissolve it still. Then also if you introduce charges to the surface, it's difficult. But it's definitely something worth trying. Of course, it would be ideal if you could increase the amount of ionic liquid compared to the DMSO, but then you already see that the intensity of the thickness of the ionic liquid compared to what we have from cellulose are already huge. So what you end up with is phasing problems, and so it's very difficult to still measure proper spectra. But I would say it's definitely worth trying the method and just trying to dissolve your samples and measure.
But it's not a walk in the park, if I understand you correctly.
Sorry?
It's not a walk in the park, if I understand you correctly. I mean, it will be a research project, not just something.
It will be a research project, but I mean also Tatiana Koso, for example, she had an article in Cellulose about oxidized celluloses and the analysis by NMR. So maybe she would be also definitely a person to contact, because it's really the NMR method is broadly applicable to many different types of derivatives, but it's always a bit of research still that we need to invest there. So it's always like really trial and error if we can dissolve it, depending on the DP, depending on the modification that we have, and also what we want to observe.
Yes, so let's see if we have any other.
We have 2 questions in the Q&A.
Yes.
Do you want to take them, or should I try?
Try. You go ahead.
We can also let the persons.
Yeah. Okay.
Ask them yourself. So if we start with Valentin Beyer, you want to?
Hello. Do you hear me?
Yes.
Oh, excellent. Yeah, I was wondering with these reducing end groups, because I recently saw a few papers where they use Passerini reaction, for example, which requires aldehydes and ketones. If you could apply this to the reducing end group to modify cellulose materials.
Yeah, certainly. I mean, there's a whole range of different reactions that would be still possible. So it's just based on the creativity of the person that synthesizes something. But it's certainly, I mean, at the moment, it's really basically limited to 4 different reaction types. But I'm very, very sure that there's a lot of possibilities still. As long as you can really like ensure that you have really selective modification at the reducing end and no side reaction in the surface. Yeah, sure.
Okay, cool. Thank you.
We have also a question from Hampus Karlsson. I allow you to talk. You can say.
Hello. Thank you for a nice talk. Yes, I had like 1 or 2 questions. The first thing I was thinking about, like the exchange between the ring openings, the closed and the open form. Can you see that like in a rosy spectrum, or it's too low abundant to see such exchange? And that, I guess, then my second question was, I mean, how low abundant are the modifications, so to say?
Yeah. So in principle, what is said is that in water, in aqueous solution, the abundance of the aldehyde group is below 1%. It's 0.002% or something like that. And the speed of like the mutter rotation or the kinetics depend on the solvent system. So for example, if you use DMSO, you slow down the mutter rotation. And by that, maybe you could observe it, I think. But I mean, of course, if we modify the reducing end group, then we have the open chain form, then we can observe our modified reducing end groups. But I think with NMR spectroscopy, you can see the different anomers. So you can see the different like positions of your OH group of the hemiacetal in NMR spectroscopy. That's what you definitely see.
Okay, thank you.
Any more questions or comments?
Not in the Q&A, and I can't see anyone in the chat, Lars.
No.
Do you have one, or should I take?
No, you take one. I had some more, but we can.
Yeah, it was just a little bit about when you do this DP determinations on pulp. Can you distinguish between what has reacted between of the hemis and the cellulose units?
Oh, it depends on maybe where you would identify it in the spectrum. So where did I have this? It really depends if you say like you want to distinguish modifications on the hemicellulose and the cellulose fraction. What we have been doing is that we have dispersed, for example, cellulose sample just in DMSO without the ionic liquid electrolyte, and then sometimes after modification you have also solubilized the hemicellulose fraction and then just adsorbed on the cellulose, and then it also like dissolves in the DMSO, and you can nicely characterize it without characterizing the cellulose. This is something that we have been doing for really identifying where it is. You could use potentially like 2D NMR methods like HSQC or HMBC, but it really depends like the signal assignment, like where are your signals, how well are they resolved, and how complex is the modification that you have and the derivative that you get. So this is also why we very often use our model compounds, because then you can clearly really compare the signals that you get from the model compound and for the cellulose, because especially with lignocellulosic pulps, the complexity of the NMR spectrum gets even larger. And it's sometimes really challenging actually to properly assign signals. So yeah, I don't know if this responds to your question. But yeah, it is really challenging. I mean, it's a very nice method for molecular analysis, but you definitely need someone who really knows like what he's doing, like with assigning signals from NMR spectra.
Yeah, thank you.
I also had a short question on your figure, on your slide number 6.
Going back to it.
It was just a small detail. So is there a reducing end group at the kink there, or is it a contamination?
Oh, I don't know. I don't know what they have described. Maybe it's a contamination. I don't know, but I mean, it might be, of course, like we always, when you have these models of cellulose nanocrystals, we always imagine them as very like clean cuts at the reducing ends. But we also don't know, of course, with this chemistry, do we really have them only present on one end, really?
Yes.
I mean, of course, due to the cellulose chain, of course, and the biosynthesis. But I mean, we don't have an ideal substrate. It's still a bio resource or a biomaterial that we modify. So yeah, who knows what they have done there?
It can be a problem and a possibility, both of them.
Yeah. It can be a problem and a possibility. That's totally right.
Yes.
It's maybe the same because people have asked me, like, can they use reducing end modification also in cellulose nanofibers? That might be even more challenging because I still have my dislocated or amorphous fraction. Maybe they are also still accessible to the chemistry that I'm using. So maybe I have then more like a patchy modification rather than Janus type modification.
I was also thinking about coming back to the molecular mass or the DP determinations. Have you, or maybe that's not the question to you, but maybe to Tatjana, have you tried to combine hemicellulase treatment of fibers before making the DP of the cellulose, or is there other?
I don't think that they have combined this. I mean, Tatjana was working with Alistair largely, and they're really experts in modification, in chemical modification. I think that could be a really nice idea to really discuss with them. And
you have to do that. Yes, that's good.
Yeah.
Any other further questions? Yes, we have from Amit.
Yeah, there seems to be also something in the chat.
Yes.
Yeah. Amit, you could talk it. You could say it yourself if you want to.
Hello, can you hear me?
Yes.
Yeah, thanks for the very wonderful talk. I have a curiosity about the sulfates present on CNC. So our CNCs are like free of sulfates, or if they have sulfates, what is the counter ion? Are they containing protons or the sodium?
I mean, we are always using them in the sodium form for several reasons, because after freeze drying, you can redisperse them, which is not possible if you have the protonated ones, and they're thermally stable. Because what we observed is when you have like protonated sulfuric acid half ester groups, then you have hydrolysis, self-hydrolysis of the cellulose from a temperature of 50 degrees on. And this is really problematic, and especially for me, because I use them freeze-dried and I redisperse them, it's impossible to properly redisperse protonated sulfuric acid hydrolyzed cellulose nanocrystals.
Okay, thank you for the answer.
So always ion exchange is really the safe bet there. I would always ion exchange them if you plan to try them.
And can I have one more question?
Of course.
Yeah, because we do chemistry mostly on the sulfate when they have proton. So I have experience like my batch, we usually store the sulfated CNC at 4 degrees Celsius to avoid any desulfation. But I have seen like the batch almost like kept for 6 or 9 months. When I took FTR on them, so I have seen trace of like carbonyl peak on them.
Okay.
So is it more of like, is it because from the like reducing the cross-linking happening between the like reducing and the hydroxyl groups, or like it's like
you mean if there is a reaction between the reducing end groups and the surface hydroxyls?
Yeah,
I don't think so. I mean, maybe it's really more that you have like self-hydrolysis or something. I would really recommend always to if you store them for a longer time, to really exchange the counter ion.
Okay.
Yeah, I think that's really the safe way. So we have at Aalto, we have kind of like, it's actually something that everyone learns when they start working with cellulose nanocrystals. If they come into our labs, the first thing they learn is actually the hydrolysis and the production of cellulose nanocrystals. And it's kind of a standard protocol, so we are all using the same.
Okay, thank you.
You're welcome.
Any more questions or comments?
Not in the chat or Q&A. Do you have?
No, I'm kind of run out of my questions.
I had just a very technical question. I saw on one of your slides that you used 65 degrees. Is that a risk that you use so high temperature, or is it not a problem?
I mean, the 65 degrees is just for keeping the viscosity during the NMR measurements low. Otherwise, you have really like the throttling problems of your signals. And it is like a risk for certain probes. But this is also like depends on the whole, like, because we use for some experiments really long pulse gradients. And this is more problematic combined with the high temperatures for certain probes. It's something that an NMR expert, based on the instrument that is available, really has to check. I know that for certain instruments at Aalto, it's not really ideal. Depends on what they're like defined for. And it's really for dissolving the samples properly, and also for transferring them, because if you transfer it after dissolution into the NMR tubes, you really have really high viscosity. So it's actually quite challenging to handle the samples sometimes.
Super, thank you.
Yep.
You're welcome.
We don't
we do have.
We do, yes.
I do have one question more. I'll allow you to talk. One raised hand from the audience.
Interesting.
I don't know if it's a sing con name. Would you like to ask your question? I've allowed you to talk.
Can you now hear me?
No, now we hear you.
Okay, finally. I just So I'm Jari Sinkkonen working with NMR at Stora Enso, and just a continuation from this Annette's question about this temperature. So, for example, we don't have any cryoprobe, so it's not a problem to go like a higher temperature. So would you, in that case, recommend to go higher temperatures if it is not a problem with the instrument? Because then you could get lower viscosity.
Yeah. This really depends on the stability of your samples. So as I mentioned, like you have a basic electrolyte, and what we observe, for example, in certain cases when we have esters, is that we actually hydrolyze our ester bonds. And it really depends on your sample. And I'm sure that Alistair has probably tried out like many different conditions, and the optimal they found was really the 65 degrees. So as a compromise between viscosity and sample stability. But maybe you could try it depending on what you have.
Yeah.
It's certainly maybe an idea to try for if you have pulp samples, for example.
Yes. Okay, thanks.
Yeah, thank you. But these are like all these questions, as I mentioned, like the protocol article was really meant to be like for this, to really say, okay, we have really nicely described every step for all these things, and also even for NMR beginners, how to treat NMR spectra with topspin, for example. Like everything is really, it's a huge thing. And hopefully really published soon, but yeah, so I hope this really helps a lot of people as a guide to use this method.
Definitely. Well, if we don't have any more questions, we thank you once more, Katja, for a very nice talk and for taking time to be with us, and also wish you best of luck when setting up your own research group now in Freiburg. And let's stay in contact. Yes.
Definitely, yeah. Thank you very much for the invite.
Thank you so much.
Thank you.
Thank you everyone who has been following this webinar. There will be one more webinar in December in this FibRe and Treesearch online seminar series, and then we will have Paul from IL. So hope to see you again in December. So with that, we close the webinar for this time. Thank you very much.
Thank you so much.
Thank you. Bye.
Yeah.
See you. Bye-bye.
Katja, you can stay, I think.